Magnetic force on a current-carrying conductor. As a result of the Lorentz force on a moving charged particle, we will see that a current-carrying wire also experiences a force when placed in a magnetic field. The net force is the sum of all the forces acting on each moving charged particle. So let's take a segment of this current-carrying wire here. Now, the positive charges, the current direction is basically defined as the direction in which positive charges would move. Actually, it's the electrons that are moving to the left-hand side. So it appears that positive charges are moving to the right, even though they're not. But so let's say that we have positive charges carrying the current here. So they have a drift velocity Vd moving to the right, and this current carrying wire has a length L, and it is placed inside a uniform magnetic field which is pointing into the page. Now, if we use the right hand rule, point our forefingers in the direction of the current, curl them towards the magnetic field which is into the page, and our thumb will point in the direction of QV cross B, which is the Lorentz force acting on this charged particle that will be pointing up. So the average magnetic force exerted on a charge moving in the wire will be Q drift velocity cross product with the magnetic field. And as a result of this, all of these charges feeling this force, it will appear that there will be a force that is going to be acting on this segment of the conductor which has length L. The volume of this segment is going to be the cross-sectional area A multiplied by its length. So the volume is A times L, and the number of charges included in this segment will be the number of charges per volume N multiplied by the volume of the segment A times L. Okay, so with that, we will have the net force QV cross B, that's the force on one charge. So we have Q drift velocity cross product with magnetic field pointing on one charge. The number of charges is charge density multiplied by the volume NaL, and since we know that current is equal to NQV drift times A, so this is charge density, the charge per particle drift velocity times A. This is basically equal to dq dt, remember. The volume is basically A times dx is volume, so they cancel. So we will be left with charge divided by time here. Time comes from velocity, so it's dq dt. So it's nqv drift times A is the current. So if I substitute that for current, nqv drift times A is current, I'm left with the current L vector cross with B, where L vector has magnitude L, but it's pointing in the direction of the current. So this is going to feel a force IL cross B. Now, if I go back and look at a current carrying conductor, I will see that when it has no current, there will be no deflection in the wire when it is placed in a uniform magnetic field. For example, in between the two poles of a magnet, a horseshoe magnet here. When we have a current, now the current is in this direction, drift velocity cross with B. So if you point your fingers in the direction of the current, or L vector, four fingers, curl them towards the magnetic field into the page, you see that the thumb points in the direction of the magnetic force, so the wire will deflect to the left. If the current direction is reversed, then we have four fingers pointing down, and then we curl them towards the magnetic field into the page. The magnetic force is to the right, so it's going to be deflecting to the right in that case. Okay, so as I said, L is a vector that points in the direction of current. It has the magnitude, which is the length of the wire. Now, if this is not a straight wire like this, if it's an arbitrarily shaped conductor, what would happen? Now, if you look at any small segment of this wire, you can say approximately this is a straight wire in this region. So for that region, the force acting on it will be I, instead of L cross B, the length of this section, ds cross with B. So from A to B, if I integrate all the forces acting on this, then I will find the net force acting on this conductor. So it will be I integral A to B ds cross B. So all straight segments that have length ds cross product with magnetic field, and this is a vector summation. Integrate from A to B, we obtain, multiplied by current, we obtain the force acting on this wire. So this dFB is the magnetic force exerted on a small segment of vector length ds. So we have talked about the magnetic force acting on a current carrying conductor. We have seen that it's due to moving charged particles within the conductor that feel the Lorentz force QV cross B. If we look at a length L of this conductor, cross-sectional area, uniform cross-sectional area A, placed in a uniform magnetic field B, the force acting on this wire will be equal to IL cross B, because the current is Q and QV drift times A, and we look at the total number of charges NAL within this section, and it's going to have each of the charges will feel this force QV cross B, so we multiply it by NAL to find the net force, which is IL cross B, where L is a vector that points in the direction of the current with magnitude L. This will be generalized for an arbitrarily shaped conductor. For small sections of this conductor where the conductor will be straight, we have I ds cross B is the force acting on that segment. If we integrate from the beginning to the end of the conductor, we find the net force as I integral A to B ds cross B. Now this ds is a vector which points in the direction of the current and it has a vector length ds.